1, 2, 3, 4, 5, 6. Hello, everybody. Let's just make sure the tablet's working. Hello, and that's working. And then that is working, I think. Hold on. I think I'm live. Yes, okay, live. So today I only have 2-ish hours before I gotta go. So we're just gonna do questions based on this week's assignment and questions based on the practice assignment. I'll make another one of these videos for the final exam prep. So I'll go through on that one. I'll go through the midterms, and then I'll also go through the practice final. But this all stuff needs to go. Okay, so let's start on page 294. This is on momentum and angular momentum. Start with question 8. So if you have any questions, you can ask them in the live chat. Like I said, I've got to go in 2 hours, so we're going to try to make this quick. Question 8 goes like this. Really? Question 8? 294. Okay, there you go. Sorry, wrong question. It says a 60-gram tennis ball with an initial speed of 32 meters per second hits a wall and rebounds with the same speed. Figure 9.4 shows the force of the wall on the ball during the collision. What's the value of F max? What's the value of F max, the maximum force of the contact during the collision? Oh, I get it. Okay, this question's fun. Okay, so here we go. I'm going to copy out the diagram we see in the book. It starts at 0. Maybe I should put this on a edge. There you go. Okay. So, in 2, it goes to 4, and then 6. And this is in time in milliseconds. And it comes up like this, goes over like this, and then it comes down like that. Okay, so it gives us the initial speed plus 32 meters per second. The mass is equal to 0.06 kilograms. And it also gives me the final speed. It says it bounces off at the same speed, so obviously going the opposite direction. How do we, and then it's asking what the highest point here is. So how do we figure out what's the relationship between all these things? Before I go on too much further, let's see if I can, give me a second here. Right, I think that'll increase the speed of the thing. Right now the stream health isn't very good. Okay, so what's the relationship between these things and this thing? Well, it's not like it's a constant force. If it was a constant force, you could probably, even if you didn't know anything, use acceleration and say constant force generates a constant acceleration. If I knew how much time the thing took, I could figure out how much force it took to accelerate between these two velocities, but I don't. One thing I can't calculate, though, is the impulse, which is the change in the momentum. Momentum final minus momentum initial, so the final momentum is 32 times 0.06, and the initial one is 32 times 0.06. This is a negative velocity, and this is minus a positive velocity, incidentally. So you get minus 3.84 kilogram meters per second. Okay, so here's the fun part. The impulse corresponds to something on a force versus time diagram. It corresponds to the area under here. Okay? So whatever the maximum height here is, the area under here corresponds to minus 3.84. Don't worry about the sign. Okay, so what's that area? I'm going to divide this up into pieces. The first piece is a triangle. So this area here is going to be, oh geez, that's gross. I'll do it like this, A1, A2, A3. So the area 1 is a triangle. So it's going to be 1/2 the base, which is 2 milliseconds, 0.0002 seconds, times the height. Area 2 is a rectangle, so it's the width, which is 2 milliseconds, times the height. A3 is another triangle, so it's 1/2 the width times the height. So the A total is going to be 3.84, but that's also equal 1/2 0.002 times F max plus 0.002 F max plus 1/2 0.002 F max. So let's add all of them up. That's 0.004 F max is equal to 3.84. So F max has to be equal to 3.84 divided by 0.004. 960 newtons. See that relationship? This type of question can totally be on the final. That's a great question to ask on the final exam. All right, question 22. How are we doing for time? We're doing okay. A 71 kilogram baseball player jumps straight up to catch a line drive. So he's in the air. Okay. If the ball, which has mass 0.14 kilograms, and the baseball player has mass 71 kilograms, this ball is moving horizontally at 28 meters per second. Okay. It specifies that the baseball player is at the highest point of the leap. Why does that matter? It's because we're going to use conservation of momentum to answer this question. And to do that, we need to know the momentum of the ball, which is right there, but we also need to know the momentum of the baseball player. So why did they specify that he's at the top of the arc? It's because at the very top, his velocity is 0. And he's not jumping horizontally, evidently, too. So P total is going to be P the ball plus P the player. So the ball's mass is 0.14 and its velocity is 28. The player's mass is 71 and its velocity is 0. So that's 3.92 kilogram meters per second. And so after they catch it, they're both going to have the same velocity. So the total momentum is going to add up to the same. It's going to be the ball's mass times the ball's velocity plus the player's mass times the player's velocity. And like I said, both of these values are the same. Alternatively, we could just say the player and the ball are one object with a mass of 71.14. Anyway, VF is going to be equal to 3.92 divided by 71.14. .055 meters per second. Yeah, that's not very fast. Okay. 28. A 20-gram ball of clay traveling east at 2 meters per second. Let's draw it. It's going east. Collides with a 30-gram ball of clay traveling 30 degrees south of west. Oh, geez. So here's west. 30 degrees south of west is that way. And it's going 1 meter per second. And they collide. How are they going to collide? I guess this is probably the wrong arrangement. They're probably going like that. So this one has mass 20 grams, and this one kilograms, and this one has mass 30 grams. Okay, and so after that they make some big amorphous ball with some other momentum, with other velocity, and I want to figure out the components of that final velocity. So the deal here is that momentum is a vector, P total PA plus PB, which is kind of tricky. So instead of talking about it this way, and I will, essentially, I'm going to talk about it in terms of its x components. Oops. Its x components and its y components separately. Because as we know about vectors, their components will be conserved separately. Okay. So the momentum of ball A, it's moving 2 meters per second to the right. So that's the mass times the velocity plus 2 meters per second. Kilograms, meters per second. All right. In the y direction, 0.02 times 0, because it's not moving in the y direction. What about this guy, though? I need to decompose that initial velocity in terms of an x component and a y component. And I'm going to do it using trigonometry. So the top one is 1 times cosine of 30. Make sure your calculator's in degrees. So this is minus 0.866. And 1 times sine of 30, that's minus 0.5. It's minus because you're moving to the left, and it's minus because you're moving down. So this one will be 0.03 minus 0.866. And this one will be 0.03 times its velocity minus 0.5 kilogram meters per second. All right. And then I added up to find the total. P total in the x direction, P total in the y direction. So this is plus 0.014, and the other one is minus 0.015. Okay, so that's the total momentum of the system, and after they glom together, they're going to have the same momentum. So this is going to be, the total mass here is 0.05, it's 50 grams. And this is going to be v in the x direction, and this is going to times v in the y direction. All right? So we just solve these. 0.014 divided by 0.05. 0.28 meters per second. And in the y direction, it's minus 0.3 meters per second. Okay, and that's the final answer. That's 28. 32. What's the angular momentum about the axle of the 500-gram rotating bar? Okay, so let me draw the rotating bar. Here's the rotating bar. It's 2 meters long. and it's 120 rotations per minute. Okay, so to answer this question, I need to know the moment of inertia of the rotating bar, and I'm going to look that up, and I encourage you to do the same. Wait, we did this a while ago. Hold on. Rotational motion. There's torque. Okay, so you can look up your formulas on page 224 of the textbook. In this case, this is going to be a thin rod of any cross-section about the center. So it's going to have formula 1/12 times m times L squared. So the mass here is 500 kilograms. Okay, so 1/12. The mass is 500 kilograms, so 0.5 kilograms. And the length here is 2 meters, which is 2 all squared. 1 divided by 12 times 0.5 times 2 times 2. 0.166. All right, so 120 rotations per minute. I want to find the angular velocity. So I want it in seconds. 1 minute has 60 seconds, and I want it in radians. 2 pi radians for 1 rotation. .57 radians per second. All right. So the angular velocity is angular momentum is the angular velocity times the moment of inertia. So it's going to be 12.57 times 1.66. .09 kilogram meters. This is in meters squared for kilogram per second. All right, that's how to do that one. Question of 32. Let's do question 34. Divers change their body position midair while rotating about their center of mass. So, in one dive, a diver leaves the board with her body nearly straight. Like that. They're diving. And tucks into a somersault position. Okay. If the moment of the inertia of the driver in a straight position is 14 kilogram meter squares, and in tuck position it's 4 kilogram meter squared, by what factor is her angular velocity when tucked greater than straight? What are they asking for? They're saying, okay, we're going to compare angular velocity tucked and angular velocity straight. Right? And so they're saying showing their velocity is, we're looking for a number here. Or alternatively put W tuck divided by W straight gives us a number. How do we figure that number out? Well, it's fun. So this is an angular momentum question. Angular momentum is conserved. So the angular momentum when it's tucked is the same as the angular momentum when it's straight. And that means omega tuck times I tuck is equal to omega straight times I straight. I want to build this thing out of this thing, so I'm going to divide both sides by omega straight. So it's tuck divided by omega straight, and that gives me I straight divided by I tuck. So it's 14 over 4, 3.5. Well, that's faster. Okay, next question, 43. Question 43 goes like this. 140-gram baseball is moving horizontally to the right at 35 meters per second when it's hit by the bat. The ball flies off to the left at 55 meters per second with an angle of 25 degrees above the horizontal. What's the magnitude and direction of the impulse that the bat delivers to the ball? Okay, so the ball comes in like this at 35 meters per second. And then it gets hit. And then after it gets hit, it ends up moving this direction, 55 meters per second at an angle 25 degrees above the horizontal. So the question here is how there's a force. We know how much time passes between them. Oh no, wait, we don't know the time. It's asking about impulse. Okay. So the question here is essentially, how has the momentum vector changed? P final minus P initial. And so to do that, I need to find the momentum vector final and the momentum vector initial. Okay, so the initial momentum vector is, I know the velocity in the x direction is 35 times the mass. The momentum in the y direction is 0. Wait, hold on. Yeah, the velocity in the y direction is 0, and the mass is 14. So this is 4.90. Afterwards, I need to start by figuring out what the components of this velocity are. So I'm going to use trigonometry on this. 55 times cosine of 25. So that's minus 49.8 meters per second. That's the x component. And the y component is 55 times sine of 25. It's going up, so it's going to be plus 23 meters per second. So P in the x direction is going to be the velocity times the mass. And in the y direction, it's going to be the velocity times the mass. Minus 6.97 and 3.22. Yep. So now the change in the momentum in the x direction is going to be the final minus the initial. So it's 11.87, and delta P in the y direction is 3.22 minus 0. So this is the impulse vector. Okay, so now that was 43 times for 59. A 1-gram bullet is fired into a 10-kilogram block of wood at rest on a wooden table. The block with the bullet embedded slides 5 centimeters across the table. What was the speed of the bullet? You know, I think this is a momentum question, and they don't give me the they give me that it slides 5 centimeters across the table, but that's no indication of the speed, because I don't know what's slowing it down. Yeah, I know how far it takes to decelerate, but I don't know the rate of deceleration, so I can't use that to figure out what the initial velocity is. Question 59 might be fun, but I can't do it based on the information I have. It says it's interactive on the internet, so my guess is, yeah, when you interact with it on the internet, they tell you what the coefficient of friction is. If I knew that, I could figure out the rest, but I don't. So, yeah, let's do it. I'm going to assume the coefficient of friction is well, hold on. I don't know. Let's just start working with it. Okay. So this thing has some initial velocity, and it's got some mass, which is 0.01 kilogram. And then there's an object, and this thing has mass 10 kilograms and velocity 0. So the total momentum of the system is going to be 0.01 times v1 initial plus 0 times 10. So it's 0.01 times v initial. After the block gets embedded with a bullet, the thing has a final velocity. So P total in this case is going to be 10 plus the bullet times its final velocity. So if I knew what this final velocity was, I could figure out what the initial velocity is. Now, if I'm given, let's suppose I'm given that the coefficient of kinetic friction on the table is 0.02. Free body diagram of this system here. There's a normal force from the table. There's a friction force pushing this way. And there's gravity. The weight is, it's in the y direction. It's 10.01 times 9.81, so it's 98.2 newtons. Normal force, the y direction, it's not accelerating up. All right, well, what do you know about the acceleration? You know the acceleration is that way, right? So A in the y direction has to be 0, so F net in the y direction has to be 0. So this has to be plus 98.2 newtons. And that means the friction force is going to be to the left, and it's going to be 98.2 divided by the mass of the thing, 10.01. So the 9.81. Okay. So it's going to be minus this. Wait, hold on. That's not right. 98.2 times 0.2. Yeah, there you go. I don't know what I was doing. So the friction force is going to be in the x direction is going to be 19.64. And that means the acceleration in the x direction is going to be that divided by the mass, 10.01. So it's going to be minus 1.96 newtons. Okay, time for some kinematics. You move this far, delta x is equal to plus, let's say 3 centimeters, 5 centimeters, 0.05 meters. Okay, and your v final is equal to 0 at that position. We'll call this position x equals 0. That's where it starts. V initial is unknown, and the acceleration is that way, and it's meters per second squared. All right, so let's plug this into the constant constant acceleration equation. Initial position is 0. Initial velocity, vi, times t, minus 1.96 divided by 2t squared. Your final velocity is 0. Your initial velocity minus 1.96 times t. So, your final position is 0.05, and now we can solve this for VI. So 0.05 is equal to VI times VI over 1.96 minus 1.96 over 2 times VI divided by 1.96 all squared. And so this becomes 1.96 times 0.05 is equal to VI squared minus 1/2 VI squared. So it looks like that. And so the velocity at this time is going to be 0.96 times 0.05 times 2 square root answer. VI is equal to 0.44 meters per second. And then you can plug that into this thing. So the total momentum is 0.443. So this is 4.43, which corresponds to a total momentum, an initial velocity of bullets of 443 meters per second, which was P total divided by the mass of the bullet. That's pretty fast. I think I did that right. Okay, so what's the next question? 59, 69. A 1 meter long massless rod is pivoted at one end and swings around a circle on a frictionless table. A block with a hole through the center can slide in and out along the wad. Oh, I see. So they're saying you put a bead on this, and it can move back or forth on the rod. Initially, a small piece of wax holds the block 30 centimeters from the pivot. No, 30 centimeters is 0.3. Initially, the block is spun at 50 revolutions per minute. So we want it in radians, 2 pi for 1 revolution, and you want it in seconds. 1 minute is 60 seconds. So that's 50 times 2 times pi divided by 60. 5.23 radians per second. Okay. When the max wax melts, the block slides to the end of the rod. What's the final angular speed? So over the wax will melt, and then the bead will go out to here. How do we calculate that? Well, this is a constant angular momentum question. So I need to calculate the initial moment of inertia and the final moment of inertia. This expression plus the initial moment of inertia will tell me the initial angular momentum, and then if I know what the final angular momentum is, I can use conservation of angular momentum to figure out what the angular velocity is. Okay, what is the piece of wax? Okay, so after reading this carefully, they don't tell me what the mass of the wax is. So if they did, I could do this question easily, but they didn't, so I don't know what to do. So I'm just going to assume that the mass is 2. If you did this question online, I would probably specify it. Okay, so the moment of inertia of it is going to be mass times radius squared for each term in it. So the mass is 2, and the radius is 0.3 all squared. The final moment of inertia is going to be the mass times the radius. It's going to move all the way out to 1 meter away, I believe. So it's 2 at the end, and at the start it's 0.3 times 0.3 times 2. Okay. So, angular momentum is conserved. How do you know this is an angular momentum question? It's in the chapter on angular momentum. But essentially, the system isn't describing any forces pushing anything around specifically. So you're going to assume that things are just rotating. It's a rotating question. There isn't any external interaction. There's no torque. So if there's no torques described or no interactions described, we're going to assume that it has constant angular momentum. Okay, so the initial angular momentum is going to be the angular velocity times the moment of inertia. The final angular momentum is going to be the unknown angular velocity times the angular the moment of inertia. So you solve these algebraically for omega. 5.23 times 0.18 divided by 2. 0.47 radians per second. Just like we would imagine it. It wants it in rotations per minute. So how do we convert this to rotations per minute? I want the units to be rotations instead of radians. 2 per radians for 1 rotation, and instead of seconds, I want it to be minutes. So there's 60 seconds in 1 minute. 0.47 times 60 divided by 2 times pi. 4.49 cycles per minute. Rotations per minute. All right, that's 69. Question 75. 75 goes like this. Disc A with a mass of 2 kilograms and a radius of 40 centimeters rotates clockwise around a frictionless vertical axle at 30 revs per second. Disc B, also 2 kilograms, but with a radius of 20 centimeters, rotates counterclockwise around the same axle, but at a greater height than disc A at 30 revs per second. Disc B slides down the axle until it runs on top of disc A, after which they rotate together. After the collision, what is their common angular speed, and in which direction do they rotate? Okay. So let's start by drawing it. Drawing your thing is always a better thing to do. Okay, so it goes around a rod. And then down here there's a different disc. All right. So what's the moment of inertia of a disc? We can look that up. Okay, so for a disk, the moment of inertia is 1/2 mr squared. So I'm going to use this. These are disks. All right, disk A and disk B. Disk A is down here. Disk B is up here. The moment of inertia is this. Okay, so it has radius 4 centimeters and mass 2 kilograms and radius 40 centimeters. And this one has mass 2 and radius 20 centimeters. So the moment of inertia at the top is 0.04 and the moment of inertia at the bottom is 0.16. And now each of these has an angular velocity. Let's go, all right. Disk A is going clockwise, so that's this direction. Disk B is going counterclockwise, so that's that direction. Okay. This one's, well, they're both at 30 revs per second. 30 revs per second. And so I want it in radians. It's 2 pi. So it's going to be, actually here, let me move all this. I got longer room down here a little bit. Okay, so it's going to be pi times 30. 188.5 radians per second. Okay, so they're going in opposite directions. Counterclockwise is usually positive, so it would be plus 188.5. And clockwise is usually negative 188.5. So we can use whether or not it's negative or positive to interpret our answer when we finally get it. So this is total moment of inertia is moment A plus moment B. Moment A is 188.5 times 0.16 minus 30.16, and moment B is 0.04 times 188.5, 7.54. So the total moment of inertia is going to be minus 22.62. And when they're rotating together, both of them will have the same angular velocity. So the angular momentum is going to be the same, but it's going to be IA plus IB is omega, final. IA plus IB is 0.2. So omega final is going to be minus 113.1 radians per second. Oh, they want revolutions per second, so I guess I'll divide that by 2 pi. Because there's 2 pi radians in a circle. So it's 18 revs per second. And that's 75. So let's move on to the next questions. The next questions I'm going to give you as a practice assignment. It's not going to be worth any marks, but it's still pretty fun. And there's a whole bunch of stuff with energy that you haven't had a chance to get any work in. And so it's pretty fun when you get the hang of it. The deal is, it's a conserved quantity. You want to keep track of how much of it you have. You can calculate how much kinetic stuff there is. Sometimes you can calculate how much potential energy there is. We'll talk as we go. Question 1. During etiquette class, you walk slowly and steadily at 2 meters per second. No, 0.2 meters per second. 20 centimeters per second for delta x is equal to 2.5 meters with a book on top of your head. So here's your head. Here's the book. Okay. So delta x is a vector. We're going to calculate work, and that means figuring out how the displacement compares to the force. Which force are we talking about? It says you're moving with constant velocity. Listen, so the deal here is that the force you're applying to it is going to be straight up, and it's perpendicular to delta x, and so the work is going to be 0. Another way to talk about that is 1/2 mass of the book times vf squared, 1/2 mass of the book v initial squared. Your masses are the same, we know. Your speed is the same, your velocity is going to be the same. Why do we know that? We know that because they tell you you're moving at constant velocity. So they're going to be the same number. You have the same amount of kinetic energy before and after, and that means no work has been done. Question 3. 2 ropes are used to lower a 255 kilogram piano exactly 5 meters from a second-story window to the ground. How much work is done by each of these 3 forces? Okay, so here's your piano, and there's 2 ropes, and there's gravity. Okay, so it starts out here, and then it ends up down here. Okay, delta x, change in position is minus 5 meters, going straight down. Okay, so they've specified the free body diagram for this, incidentally. So this angle here is 60 degrees, and it has magnitude 1830 newtons. This one has angle 45 degrees, and it has 1295 newtons. This force, gravity, has magnitude 2500 newtons. Okay, I'll call this one T1 and this one T2. So we need to calculate work 3 times in this case. So I'll do it just like we talked about in class. Work is equal to force dot dx. I'm going to start by drawing them side to side. Tail to tail. Delta x looks like that, and the force looks like that. So they're aligning, so the work is going to be positive 5 times 2500. 5,000 joules. Next one, T1. T1 looks like that. 1830. Delta x looks like that. 5. What's the angle between them? The angle is going to be 60 plus 90. So the work done is 5 times 1830 times cosine of 60 plus 90. And it's negative 7924 joules. It's negative because it's slowing the thing down. And the last one. I'll draw them. Okay, so here's 1290, and that's 45 degrees. This distance is 5, and so and that's a right angle. Don't allow. Yes, you don't want to access the microphone. So the work done here is 1290 times 5 times cosine of 45 plus 90. Minus 3. Oh, you're 1290 times 5 times cosine of 135. Yeah, I did do it wrong. Okay. Sorry, my calculator gave me a wrong answer just now. All right. So this is how much work each of these ropes did. And now you might be like, hey, wait, hold on, but the amount of energy you take out of the system is 4561 plus 7924. You took out 12,000 joules of energy, and you only gave 5,000 joules of energy. It's like, yeah, maybe the piano needed to slow down. So the piano needed to slow down, but also if it was left to its own devices, it would speed up. And so the ropes had to take this much energy out to keep it from slamming into the ground. Okay, so that's question 3. Let's do question 5. Evaluate the dot products of 3 pairs of vectors. Oh, fun. That one's 3. That one's 4. That's 110 degrees. So A dot B is going to be 3 times 4 times cosine 110. Minus 4.1, whatever it is. All right. D looks like that, and it's 5. C looks like this, and it's 4. So C dot D, there's 180 degrees between them, so it's going to be minus 20. Minus 4 times 5. And the last one, E looks like this, and F looks like this. It's 3. That's 30 degrees. And so E dot F is going to be 3 times 4 times cosine 30. .4. The dot product isn't just useful in calculating work, but mostly in this particular course we're going to use it to calculate the work done. All right. And, oh, 2 people are watching. Hello. How are you? Nobody said anything, which means that it's okay. Now it's question 7. Which has larger kinetic energy? A 10-gram bullet fired at 500 meters per second, or a 10-kilogram bowling ball sliding at 10 meters per second? Well, there's no way to know unless we multiply it. Oh wait, this is 0.01 kilogram. 1/2 mv squared. So it's going to be 1/2 times 0.01 times 500 squared. I think this is probably going to be a bigger number. 500 times 500 times 0.01 divided by 2. 1250 joules. In this case, it's 1/2 times 10 times 10 squared. 500 joules. Oh look, there's less energy in the bowling ball. Even the bowling ball is super heavy. Which one has more momentum? 500 times 0.01, that's 5. Okay, this is kind of neat. This one has more energy. This one has less energy. This one has more momentum. And this one has less momentum. That's fun, right? We just want to compare them. Just comparing these two. The question's not asking for it, but Always pays to look around. 11. A 2-gram plastic ball is moving to the left at 30 meters per second. How much work must be done on the wall to cause it to move to the right at 30 meters per second? This question's awesome. Okay, so the mass of this is 0.0, no, it's 0.02 kilograms, and it's moving to the left at 30 meters per second. And the mass here is 0.02 kilograms again, and now it's moving to the right at 30 meters per second. Okay, so you calculate the kinetic energy. I want to calculate the change in kinetic energy. Kinetic energy initially is nine joules. Kinetic energy final is 9 joules. Why are they the same? Well, I don't know, 1/2 times the mass times plus 30 all squared, that's a positive number. 1/2 mass minus 30 squared. That's a negative number, but when I square it, it becomes a positive number. So they're the same. But isn't this weird? Okay. There's a couple ways of explaining this. One of them is to just ask ourselves, how do we get from this to that? Well, one way to do it would just be to hook up a big circular tube like this. So the ball would hit this side and then travel down and around and around. What force would cause it to move like this? Well, there's a normal force from the wall, and the normal force is always causing it to accelerate towards the middle and move in a circle. But note, this normal force is always perpendicular to the velocity. They're at right angles to each other. And that means the normal force never does any work. So that's one way to do it. Another more convoluted, and I know that that's pretty convoluted, another way to explain how one turned into another, because there's lots of different ways one could turn into another, is if we imagine that there's a force, you take out your hand and you push it that way, decelerating it, and it'll move some distance. So the ball hits your hand and you decelerate it with that amount of force over that distance. Slows down to a stop, and then you reverse your motion. You start to push that way with the same amount of force until it's moving at 30 meters per second again. Okay? The amount of force that you're using to push is assumedly the same amount of force, because otherwise, if you pushed it over the same distance here, you need it to go back to the same speed it was over the same distance. So the same force corresponds to the same amount of time accelerating, same motion. Okay, so here's the fun thing. On this part of the journey, you're taking out 9 joules of energy. And in this part of the journey, you're putting back 9 joules of energy. So that in the end, it has a total of 9 joules of energy, and the total energy hasn't changed. In other words, you're doing the same amount of work, slowing it down as speeding it up, so the total amount of work done is 0. Like I said, there's a bunch of different ways we can explain this. The easiest way is to just say, calculate the energy before and after. It's the same. Get on with your life. Question 12. A turntable in a microwave oven has a moment of inertia of 0.04 kilogram meters squared. And it's rotating once every 4 seconds. So its angular velocity is 2 pi over 4. Cool. What's the kinetic energy? It's going to be 1/2 I omega squared. 1/2 times 0.04 times 2 pi over 4 all squared. .05 joules. Okay. Yeah, it doesn't have much moment of inertia, and also it's not traveling very fast. All right, question 13. An energy storage system based on a flywheel we talked about in class can store a maximum of 40 megajoules. What happens if it spins faster than that? It rips itself apart. So the energy is 4e6 joules. And the angular velocity is 20,000 revolutions per minute. I want angular velocity to be in radians per second, so it's revolutions, radians over revs. One revolution is 2 pi. Minutes into seconds. 1 minute is 60 seconds. So that is 2 times 2 times pi divided by 60. 2094 radians per second. So the kinetic energy is 1/2 I omega squared. And so the value of I is equal to 4e6 times 2 divided by 2094 times 204. 1.82 kilogram meter squared. Flywheels are fun. Incidentally, why is there a maximum amount of energy you can put in it? It's because if you spin the wheel any faster, the stuff will break. Maybe the flywheel will tear itself apart. Maybe the machinery just won't be able to successfully control its rotation. If you spin it fast enough, it'll break. But there's nothing wrong with having a high kinetic energy. Okay. Question 15. What's the kinetic energy of a 15,000 kilogram car traveling at a speed of 30 meters per second? Times 1500 divided by 2 is 675,000 joules. This is why cars cost so much, are so expensive, are so valuable, because there's lots of joules in them when they're moving. From what height should the car be dropped to have the same amount of kinetic energy just before impact? This is a gravitational potential energy question. We haven't done this yet in class, but the gravitational potential energy is mg height above the ground. So it's the mass is 1500, g is 9.81. I don't know the initial height, but I want all of this energy to turn into kinetic energy down at the bottom here. 1500 plus 9.81 times h, it's a time symbol, is equal to 675,000 joules. .9 meters. That's how high you'd have to start to get it moving that fast. Does your answer to part B depend on the car's mass? The short answer is it depends on whether there's air. If something's really heavy, drag won't be very large, even if you're moving kind of moderately fast. But you never know. So 1/2 mass 30 squared is equal to 1/5, that's the mass. Mass times 9.81 times height. Cancel, cancel. Doesn't look like the mass. No. Height's going to be the same. And so let's do question 16. The world's fastest human can reach speeds of 11 meters per second. Oh, good work. Yeah, I guess that makes sense. Usain Bolt can run it in just a little under 100 meters in just a little under 10 seconds. It increases gravitational potential energy by an equal amount to full speed. How high would a sprinter need to climb? Okay, so your sprinter is going to fall from some height. The start velocity is 0. Kinetic energy is 0. Gravitational potential energy is equal to mass. Does it say the mass? Doesn't say the mass. Mass times 9.81 times the height. So the total energy is going to be 0 plus mg h. And h is what we're trying to figure out. Down here at the bottom, v is going to equal 11 meters per second. So the kinetic energy is going to be 1/2 m11 squared. And the gravitational potential energy at the bottom is going to be 0, because the height is 0. And so the total energy is going to be 0 plus 1/2 m times 11 squared. And the total energy is conserved. So the height, you solve this, is going to be 11 times 11 divided by 2 divided by 9.81. 6.18 meters per second. Really? Cool. That's interesting. So one question you might ask yourself is if Usain Bolt here's Usain Bolt in his famous position. I think he goes like that. Anyway, if he ran at full speed and went up a ramp, how high would he go in the air? And apparently the answer here is 6.18 meters, which is incredible. I'd like to see him do that. Okay, so 72 kilogram bike racer climbs a 1,200 meter long section of road that's sloped at 4.3 degrees. How much does his gravitational potential energy change? So the gravitational potential energy is going to depend on how high that is, what the vertical change is. So I need to use trigonometry to find delta y. 1200 times sine of 4.3. So that's 90 meters. And so the change in gravitational potential energy, mg delta y, so it's going to be 90 times 72 times 9.81. 63569 joules. That's fun, right? Okay. 17. Let's do 22. Marissa drags a 23 kilogram duffel bag 14 meters across the gym floor. If the coefficient of kinetic friction is 0.15, how much thermal energy does Marissa create? This is a work question. It's Marissa. She's got her duffel bag. It's full of bad report cards. That's why she's in the gym. Okay. Um, I guess we assume that she doesn't drag it at an angle, that there's no tension. They don't quite tell you, but this question is a little bit faster and looser than you think. Um, so, long story short, though, it's all about systems and energy. If the system is the bag and the lady and the earth, fine. This system doesn't include the ground. And the ground is applying a few forces on the bag. It's pushing up a normal force like that. But given that delta x is horizontal, the normal force isn't going to do any work. The thing that will do work, though, is the friction force on the bag. So if we can figure out the friction force, we can calculate how much work the friction force does. And when friction force does work in this situation, it turns into heat. So, normal force, weight, friction. Kinetic friction, let's just not. Here, hold on, let's just do it. You've done these calculations a million times. 23 times 9.81. It doesn't really have any mysteries in it. 33.8 newtons. Okay. So they pull it with 33.8 newtons to the left. The change in position is 14 meters. So the work done is minus 33.8 times 14. Minus 473 joules. So, the friction force takes this energy out of the system. So this energy turns into heat. Does friction force always... Can friction force always do work? Yeah, friction force can do all sorts of work. Does friction force always turn stuff into heat? The answer to that's kind of complicated. Because sometimes when friction force does work, it'll like, I don't know, like just imagine you got a truck and you got a melon in the truck, and imagine that the car starts driving and the melon starts sliding back. And it's going to slide back until the melon's velocity... In other words, the car accelerates forward, truck accelerates forward faster than the melon can because of friction, but eventually they'll be traveling at the same speed. In that case, the force pushing the melons forward is the friction force. It's doing work, but that work goes into kinetic energy. So, hard to say when it comes to forces. 22. But long story short, in this case, you calculate the work done by friction, and that turns into heat. All right, 24. A 90 Newton crate slides 12 meters down a ramp that makes an angle of 35 degrees to the horizontal. When they say it has 900 newtons, I think that means that that's the magnitude of the weight. At an angle of 35 degrees to the horizontal. If the crate slides down at a constant speed, how much thermal energy is created? Okay, so this is the fun part. The deal here is that the speed is constant, okay? And that means that there's no acceleration. which means that all the forces are balanced. So what forces are there? There's gravity, there's a normal force, and there's a friction force. There must be, because otherwise it would accelerate. Okay, so we know they're all balanced, but that's not the question. The question is, how much energy is created? And the idea here is that the different forces on it will do different amounts of work. Okay, so gravity will do the work. Let's see, what's the angle between them? Delta x is 12. That's the gravity force. What's this angle? This one's 35 degrees, so this one must be 55? Yeah. So the work done by gravity is going to be 12 times 900 times cosine 55. In the end, we're going to get a positive number because left to its own devices, gravity would speed the system up. Speed up this box by this much. Okay. The friction force, on the other hand, is doing work as well. The work done by the friction force, this force, is in the opposite direction. So the work done by the friction force would be minus friction force times 12. But here's the interesting thing. Gravity's putting energy into the box. Friction is going to take energy out of the box. How much energy? We know that it's moving at the same speed at the start and at the end. And that means that delta KE, the change in the work, total work, is going to be 0. Which tells us that the work done by friction is going to be the same as the work done by gravity. How do we know? Because it's moving at a constant speed, not speeding up, not slowing down, we know that the energy given to the system by gravity must then be spent by friction. All this friction at force goes, all the work done by friction in this case goes into heat. So that is the change in heat. All that energy goes to heat. Cool. Or rather hot. That's the amount of thermal energy you generate. Oh. Question 28. What minimum speed does a 100 kilogram puck need to make it to the top of a frictionless ramp that's 3 meters long and inclined at 20 degrees? Okay, so you could do this question in a couple different ways. You can just use plain kinematics. You know, you can calculate the acceleration on it because it's only feeling gravity. So you could calculate the acceleration, and then you know that at the top of the ramp you want v to equal 0, and so do it that way. But there's a faster, better, easier way to do it, and that uses conservation of energy. What do you mean? I mean like this. The energy at the top of the ramp, the total energy, has to be the same as the energy at the bottom of the ramp. At the bottom of the ramp, so there's two types of energy in this case. There's gravitational potential energy and kinetic energy. At the top of the ramp, the kinetic energy is 0, and the bottom ramp, the kinetic energy is 1/2 times the mass times the initial speed squared. At the top of the ramp, the gravitational potential energy is, oh, you need to figure out how high this is. It's 3 times sine of 20. So it's 1.02. So the gravitational potential energy is 1.03 meters times the mass, 0.1, times the gravity coefficient, 9.81. Gravitational potential energy at the bottom is 0 because the height's 0. So that is... So we know the total energy of the system is 1.01 joules. Times 2 divided by 0.1. Square root answer. 4.49 meters per second. This is how you do it. Conservation of energy. Alright, question 34. We're trucking along here. A fireman of mass 80 kilograms slides down a puddle. When he reaches the bottom, 2.4 meters below his starting point, his speed is 2.2 meters per second. How much thermal energy has increased during his slide? That's fun. So his initial height here is 4.2 meters, and his initial speed so at the bottom here his speed is 2.2 meters per second, and his speed up here is 0. Okay. So this too is a conservation of energy thing. There's an additional problem. A person can't actually answer this question. The question is how much heat is generated. A person can't actually solve this question based on kinematics alone. We don't know what the force of friction is. You could kind of do it right now. So you could say, okay, they're not going from this position to this position. They're not going from this position to this position and only having this much speed. So you could use kinematics to figure out what the acceleration it is to start from this height and go to this height at this speed. And then if you knew what the acceleration is, you could figure out what the forces are and say, well, okay, there must be an upward friction force, and figure out what that is, and then do the work. There's a faster way. And that's to keep an eye on the total energy. Total energy, there's gravitational potential energy, and there's heat, and there's kinetic energy. Same thing at the bottom. At the top, the gravitational potential energy is 4.2 times 9.81 times 80 kilograms. So at the top there's 3,296 joules. I'm going to stay at the top. The heat is 0, not because there's no heat at the top, but what we care about is the change in heat. So it's going to increase. Kinetic energy at the top is 0. Gravitational potential at the bottom is 0. I don't know how much heat is generated, but I can calculate the kinetic energy. 1/2 times 80 times the speed squared. 193.6 joules. So somehow all of this energy went into these two. 3,296, the total energy at the top, H plus 196, H is equal to 3,102 joules of heat was generated. Poor guy. Ouch. 38. Ball, oh, it's a collision question. Collision questions are fun. They usually involve momentum as well as kinetic energy, so we'll see. Ball 1 with a mass of 100 grams is traveling at 10 meters per second, collides head-on with ball 2, which is a mass of 300 grams, and is initially at rest. Okay. What are the final velocities of each ball if the collision is perfectly elastic and perfectly inelastic? So before we go on, I need to define some terms. We'll talk about these terms next class a little bit, but actually, okay. In a perfectly elastic collision, the kinetic energies, the total initial kinetic energy is the same as the total kinetic energy at the end. In a perfectly inelastic collision, the objects stick together. So V final of object A is equal to V final of object B. So that's the distinction between the two. The deal here is, though, in a perfectly elastic collision, all the kinetic energy turns back into kinetic energy. In a perfectly inelastic, as much energy as possible has been converted into deformation and sound and heat. Okay, so let's sort this out. Ball A, kilogram, 10 meters per second. It's ball B, mass 0.3 kilograms, VI is equal to 0. So if it's a perfectly elastic collision, they're going to bounce off each other. V final. And I'll call this one U final. And the deal is that the total momentum and total kinetic energy before and after the collision are going to be the same. So momentum. So the total momentum here is 1 plus 1 kilogram meters per second. Total momentum in this case is 0.1 times VF. Oh wait, that's a minus VF. No, you know what? I'm going to leave it as V, and if it's negative, it'll pick up a negative sign. Plus 0.3 UF. So we know these have to add together to equal 1. What about kinetic energy? So this is momentum. Kinetic energy also has to be conserved. So before, 1/2 times 0.1 times 10 squared plus 1/2 times 0.3 times 0 squared. So there's 5 joules of energy. And afterwards, 1/2 times 0.1 VF squared plus 0.3 over 2 UF squared. And that's got to equal 5. So the deal is that I need to solve these two equations together. Let me make myself more space here. So I'm going to modify this particular equation, make it easier to solve. VF is equal to 10 minus 3 UF. And now I'll plug it into that one. So it's 0.1. I'm gonna take this particular formula and multiply everything by 2, and then I'm gonna multiply everything by 10. So this particular expression becomes VF all squared plus 3 UF all squared is equal to 10, 100. So this is going to be 100 minus 60 UF plus 9 UF squared plus 3 UF squared is equal to 100. And now you're going to solve this equation. Whoops, it's supposed to stay there. Minus sign. So that's going to be 0. And then you combine those two together, and it's 12. And I'm going to factor out a UF. UF, so it's minus 10 plus 12 UF is equal to 0. So there's two solutions to it. UF is equal to 0, which corresponds to the initial setup, and the velocity 0, and UF is equal to 10 over 12. Zero 0.833 meters per second, which corresponds to VF, (7.5) minus 7.5. No, hold on. So 1 minus 0.03 times 0.833 is equal to 0.75 divided by 0.1. Okay, it's supposed to be a plus. Why is it supposed to be a plus? That corresponds to it after the collision. The mass says that this one moves that way. That's interesting. Really? Same momentum. The light ball should bounce backwards. Must have made a mistake somewhere in here. If the first one was heavier than the second one, it wouldn't have bounced off. What did I do wrong here? I did something wrong. Let's see. Okay, well, let's go over the numbers again. The momentum is 1, right? And the way to write the momentum is 0.1 times VF. I don't know its sign. Times 0.3 UF. I don't know its sign. I'll multiply both sides by 10. Subtract that. So VF is equal to 10 minus 3 UF. Okay, that works. Kinetic energy is equal to 0.5 times 0.1 times 10 times 10. That's 5 joules. It's got to be the same. 1/2 0.1 V squared 1/2 0.3 UF squared. It's equal to 5. Multiply that by 2, so that's 10. Multiply it by 2 again, 10 again, it's 100. Replace that with that. So it's 100 minus 60 UF plus 9 UF squared plus 3 UF squared. And there's 100 on this side. And they cancel out. And you get this is minus 60. So 60 over 12. That's 5 joules, 5 meters per second. And then V, and then UF is, so it's 1 minus 0.3 times 5 divided by 0.1. So UF is minus 5. That makes sense. Okay. So what are the final velocities if it is a... So long story short, check your answers if they don't make sense to you. That said, you know, like I said, you can get a positive velocity for this one. It's usually a positive velocity if this one's the heavier one and this one's the lighter one. If this one's heavy and this one's light, then this one will end up moving forward. So the thing that I noticed was that this one is lighter and it shouldn't move forward after the collision, it should move backwards. So there's that. A little bit of physical intuition, huh? Alright, what if they're perfectly elastic? If it's perfectly elastic, then the momentum before is going to be related to the momentum after. I've already calculated the momentum before. The momentum after is VF. And if they stick together, they're going to have the same momentum. So the whole system is going to have 0.4 kilogram mass, VF. So in those cases, VF is 1 divided by 0.4. 2.5 meters per second. Yep. So that's what you get if it's perfectly inelastic. They both travel with that velocity. Whew. What was that, 38? Yeah, 38. All right. I might make this deadline after all. 52. A child is 20 kilograms. Is that how much childs weigh? I don't know. It's on a swing. Oh, I should check that. Does anybody have any questions? Nobody has any questions. Okay, keep going then. All right, a 20 kilograms child is on a swing that hangs for 3 meter long chain as shown in a picture. Here's the picture. Picture says that this angle is 45 degrees. And it says that this is 3 meters. Okay. What is her speed at the bottom of the arc if she swings out to 45 degrees before reversing direction? How do we figure this out? The answer is potential energy. If I knew how high this was, then I could figure out what the gravitational potential energy was. And the deal is that at any point in time, she's only going to have 2 types of energy. She's only going to have kinetic energy and gravitational potential energy. So initially, her energy, she has no kinetic energy. Wait, no. Initially, she has a lot of kinetic energy. 1/2, her mass is 20, v squared. I don't know how her speed. 0 gravitational potential energy. The final, when she's in this position, she's got no kinetic energy, and her gravitational potential energy is mass times 981 times this height. So let's focus on finding this height. I'm going to draw that thing down here in a little bit less of a... Okay, this is a pretty fun calculation. You know that this arm is 3 meters long. And you know that this angle is going to add to this to make 90. So this angle must be 45 degrees. So that length is 3 times sine of 45 degrees. .55 meters. You know that this length here is 3 meters long, so this length must be 3 minus 2.55, which is 0.45 meters. That means that you can calculate the total energy. 20 times 9.81 times 0.45. 88.3 joules. 1/2 times 20 times v squared, because these two have to be equal, so we can calculate v. .97 meters per second. She needs to go up 3 meters per second. That's fun. 52 and 55. Oh yeah. The sledder shown in 10.55 starts at the top of a frictionless hill, slides down into the valley. What initial speed does the sledder need to make it just over the next hill? This is all about energy. Again, to just make it over, your final velocity there has to be 0. That's what we mean by just over, because if this guy is any bigger than the number we're going to calculate, then you're going to make it over with some extra speed. So that's the threshold. How much energy do they have at that time? Well, they've got gravitational potential energy and kinetic energy. So the gravitational potential energy is 42 times their mass times 9.81. Kinetic energy at that point is 0. What about here? The energy is equal to gravitational potential energy is 30 times the mass times the 9.81, and its kinetic energy is 1/2 mv squared. And the idea is that this number is equal to this number. So how do we solve it? There's two things I don't know and only one equation. Well, it's true that there are two things that we don't know, but one of them is linear in m in each of these terms, and that means we can factor out, we can divide out the m. So the first term becomes 30 times 9.81, 294.3 joules, plus 1/2 v squared is equal to 42 times 9.81, 412. These aren't joules, incidentally, they're joules per meter, but whatever, we're just solving things algebraically. So minus 294.3 times 2, so that's equal to 235.4. So the initial speed needs to be 15 meters per second. All right, that's it for this particular bit of preparation. I will try to upload the solutions to the assignment, to the final exam when I and the solutions to the last midterm when I upload them a little bit later this week. So until then, stay out of trouble and be good. Be good to yourself.